Okay, so I already recorded this, but I got annoyed with how bad I was teaching, so I recorded again. So when you the main one of the things that's coming out will be about spring. So it will talk about like the extension of the spring, Hooke's law, spring constant, so on. So for a spring to extend in the first place, for a spring to even be a spring, it must have elasticity, and elasticity is the ability for the object to extend and then go back to its original shape. And then the relationship between force and spring, and no, not in spring, extension of the spring. Extension is how much did the spring get longer. Like for example, it has the original length of L0, and then after you extend, it becomes L1. So the extension is the difference between these two lengths. So when you apply a certain force, it will extend the spring, and that is Hooke's law. Hooke's law says that the extension of the spring is directly proportional to the force applied on the spring. So if you extend the spring, if you apply some force on the string, it will become longer. The string will become longer. So that is extension of the spring, and that is Hooke's law. And the thing is, it increases linearly. Linearly means that it's a straight line. I'm not going to explain why it's a straight line because that's going to make it confusing. But the formula for force is F equals to Kx. So the F is the force that you apply on the spring. X is the extension of the spring, and K is the spring constant. The spring constant is the constant which shows you how many force do you need to extend it by a certain amount of distance. For example, 5 Newton per cm, 5 Newton per mm, 2 Newton per cm. So the spring constant shows you how many force you need to extend it by a certain amount, because springs do not share the same spring constant. Some of them are harder to extend, some of them are easier to extend. So I'll get to that part later. For now, we'll talk about how do you find the spring constant. You divide F by X. If you divide F by X, it looks very similar to the gradient of the graph. So to find the spring constant, you can divide force by its extension, or just the gradient of the graph. And then for elastic potential energy is the energy that the spring has to go back to its original position. So the formula is work done, which is Fs. But since we're talking about the whole extension process, so at first you have 0 force applied, and then in the end you have F force applied. So when you add them together and divide by 2 to find the average, the formula is 1 over 2 Fx. So that is the formula for the extension of the spring. And then if you remember, F equals to Kx, so the overall formula is 1 over 2 Kx squared. So yeah, work done is Fs, right? Fs. F is the force applied, so you want to find the average force. And then S is the distance. So the distance in this case is the extension of the spring. And then F equals to Kx, so you sub it in, then you will get 1 over 2 Kx squared. Yeah, I did some explanation, but then I failed. So I'm going to mention it again. Okay, so the main factors that affect the spring constant is number 1, material, number 2, length, diameter, and thickness. When your spring constant increases, so if it goes higher, that means that it is harder for you to extend the spring. If the spring constant is low, that means it is easier for you to extend the spring. So like for example, I apply 5 Newton on a spring. Let's say the spring constant is 5 N per mm. Then every 5 Newton, I will only extend it by 1 millimeter. But if I have a spring constant of 1 Newton per mm, then every 5 Newton, I will extend it by 5 millimeter. So you see here that even if you apply the same force, this one extends less because it has a higher spring constant. And this one extends more because it has a lower spring constant. So the lower the spring constant, the longer you can extend it. And the higher the spring constant, the harder it is to extend the spring. So material, it depends on the material. For example, plastic or metal, length of spring, if it's shorter means it has a higher spring constant. And longer means it has a lower spring constant. For diameter is in the spring gun, the gap between the spring punya, the gap between these two. So that's the diameter. The larger the diameter, the lower the spring constant. But the smaller the diameter, the higher the spring constant. And then lastly is the thickness. So if the thickness of the wire is the wire itself linear thickness. So if your thickness is like this, compared to this is higher thickness. This is lower thickness. So if it's higher thickness, that means it has a larger diameter. If it has a larger diameter, it has a higher spring constant. It has a smaller diameter, it has a lower spring constant. Okay, now the main part of the topic, other than Hooke's law, is the extension of springs applied in a spring system. A spring system is a combination of springs together, and it works similarly to light. Where if you remember in light, if you have a parallel circuit, the voltage will spread like the same to both. But if it's series, each light bulb will get a certain amount. So in this case, the spring, if you have two springs arranged in series, the force will be applied throughout the whole thing. From top to bottom, it's all 12 Newton. So here's 12 Newton, here's 12 Newton also. So that means each of this extend by a certain amount. So the total extension is 2x. Because if you know that each spring extends by x, then two springs will extend by 2x. Secondly, if you have them arranged in parallel, which means that they are next to each other like this, if you extend it, the 12 Newton gets applied to both. So it shares the force. So each spring gets less force. Since it gets less force, it extends less. So when you have a springs arranged in parallel, the extension is halved. Not half. In this case, it's halved. The number here actually depends on the number of springs. For example, if I have 3 springs, right, and then I extend it by 12 Newton. So this spring gets 12 Newton, this spring gets 12 Newton, this spring gets 12 Newton. And then this spring extends by x, this spring extends by x, this spring extends by x. So the total extension will be equal to 3x. And then for springs in parallel, if I have 3 of them, like that, and then I try to and I apply a force on this. If I try to apply a force on this, each spring will experience a certain amount of force. So if I apply 12 Newton, then it will be evenly separated. So it's 4, 4, 4. So since it's less force applied on each spring, then they extend less. So if it's series, it's longer. If it's parallel, it's shorter. So you don't know about that. And how shorter, how longer, it depends on the spring. So if it's 3, divide by 3. If it's 2, divide by 2. If here is 4, then times by... If this is 4 springs, then you have to times by 4. If here is 3 springs, you have to divide by 3. So I'm going to do an example of a question. Let me just... Okay, so for 50 millimeter, the spring itself is 50 millimeter in this example. So this whole spring without extension is 50 millimeter, and then every 12 Newton it extends by 6. So every 12 Newton it extends by 6. So 6k, because we want to find the spring constant. So k is equal to 12 divided by 6, which is equal to 2. So 2 Newton per millimeter here. That means every 2 Newton it extends by 1 millimeter. So now that you find the spring constant, now I'm gonna go immediately to arrangement C, because arrangement C is the hardest one. So you have 12 Newton carrying this whole spring system downwards. So when you have it carrying the whole thing downwards, remember that it is applied throughout the whole thing. So here is 12 Newton, here is also 12 Newton. But since this thing has 3 springs, the 12 Newton is divided equally among these 3. So divide by 3, so here is 4 Newton only. Or you can just divide the extension immediately, because you know that if you know that for one spring it extends by 6 millimeter, then for a spring system of 3, it will be 6 divided by 3. So it will be 2 millimeter. So this will extend by 2. This will extend by 6. But if you're gonna play it safe, if you know the force, you find the total force first. You find the force, you divide it by the number of springs, and then you use F equals to kx to find the formula, to find the extension. So you have to be careful lah. Sometimes it will ask the extension of each spring. Sometimes it will ask the total extension. Sometimes it will ask the total length. Okay, tension means force, by the way. This is force. So tension is the force of the exerted on the spring. That's why I said that the force is distributed equally among this whole thing, because the whole thing is tension. The whole thing is affected by tension. So again, if we're talking about extension of each spring, then you have to find how much does the spring extend for each spring. So for here it's 6, here it's 2, 2, 2. Total expansion, since you're trying to calculate the total extension, since you want to find the total expansion of the springs from top to bottom, even though here it's 2, 2, 2, they are all at the same area. So the whole thing is only 2. So 2 plus 6 is 8. So the extension is 8. And then the total length. So when you have the total length, you have to add the original length by 8. But remember, there are 2 sets of springs. There is 50 here and 50 here. So you have to add 50 twice and then add by 8. So you get 108.